Thanks for coming out to support our students. We're going to be presenting the AGU. We have a lineup today, so we have 3 speakers. There might be a little time constraint that we'll have to deal with, so maybe keep it to 1 or 2 questions after every speaker. Yeah, I'm going to read the bios. That's going to take a little second too, because we have 3 to read. But first up, we have Melissa. Melissa's a PhD student in OE at UNH. She earned her bachelor's in physics and mathematics in 2019 from the State University of New York at UNH. Melissa's research under advisor Dr. Diane Foster focuses on utilizing field observations and novel instrumentation to improve the overall understanding of sediment transport processes in the nearshore environment. After that, we'll have Andrew. Andrew received his undergraduate degree in civil engineering from the United States Coast Guard Academy. Following graduation, he served for 2 years as a deck watch officer on CGC Escanaba and 2 years as the executive officer of CGC Donald Horsley. I didn't butcher those names. He's now funded by the Coast Guard and received a master's in ocean engineering from UNH. Having completed his mapping certificate requirement with CCOM, he's now studying seafloor sediment acoustics with Dr. Gabriel. And third up, we have Elijah. Elijah Rousseau earned a bachelor's in physics and conservation biology with a minor in mathematics from the University of Toronto in 2022. Elijah is in the process of completing his Master of Science in Ocean Engineering under the advisement of Dr. Tracy Mandel. His work focuses on the hydrodynamics of sediment transport in the Hanson Seabrook estuary. Okay, so now we can get started, please. Welcome, Melissa.
Thank you for the introduction, and hi everyone, happy Friday. So hopefully this is 10 minutes, we'll see. It's a little long of the last time I was looking at it, but so we're going to talk a little bit about wave-induced pressure gradients, specifically within nearshore sediment beds. Okay, so when we think about the beach, we can think about waves propagating over our beach. This picture here makes the sand look continuous, but we know that's not true. It's made up of sand grains, water, air bubbles. It's going to be a very dynamic environment. And as the waves propagate, they actually induce forces on the bed, both in the horizontal and vertical. Specifically, I'm going to focus on the pressure gradient forces that are induced by the waves, but there's also things like shear stress from the horizontal flow. And then all of those, both these pressure gradients can lead to implications for the sediment. So we have things like instantaneous motion and momentary liquefaction caused by each respectively. And we're going to talk a little bit about some of those today. So I'm going to start off with the vertical pressure gradients. The bulk of my work so far has been on this. Many of you might have seen this before, or parts of this before, as well as we published a paper on this recently. So as kind of mentioned in my bio, my focus is on the field observations with the novel instrumentation, so that's what we're going to talk about first. So making these pressure observations in the nearshore environment, I've designed an instrument that we call the pressure stick. Many of you may have seen this before, be carrying it around the building or into the tanks or whatnot. And it is an array of vertical pressure sensors. So there's 8 pressure temperature sensors spread out about 70 centimeters along the length of the pipe. There's this little schematic of what they look like in real life. The white is the pressure sensor membrane, and we pot them in hex head screw bolts we then screw into the pipe. This whole system is fully autonomous, so there's the top holds all the electronics, as you can see. All of that stuff we do in-house here. And because it's autonomous, so there's no cabling or anything like that, we put some batteries in, we hook it up, and we let it go at the beach for a bit. There's one clock as well, which is important, so all of the pressure sensors are synced in time, which is good. And then it's rapidly deployable, as I kind of said already a little bit, but it only takes 2 people to get this into the sand at the beach. And then we samples fairly fast at 18 hertz, which is also important as we look at waves and such. And additionally, we've shown that it can resolve these vertical pressure gradients that we're interested in. Here's a schematic from the paper we published, again showing the spacing of the sensors. We like to have 4 in the water and 4 in the sand. That's the color coding there. And then just an example of what it looks like at the beach. And then the schematic of the sensors again. Where we've done the work so far, I mean, you all know New Hampshire well probably, but for those who might not, we have 13 miles of coastline, so we do our deployments down at Wallace Sands Beach. This area is macrotidal, right, so we have a large tidal range, so we can deploy at low tide, and by high tide our instruments are covered. The beach we work at specifically, Wallace Sands there, is medium sloping, so not a large gradient as you go from the back of the beach to the water in the cross-shore direction. It's also very uniform in the along-shore direction. And this also helps with the waves coming parallel to shore, which is interesting to work in and also helpful that we can assume or make assumptions in the alongshore direction about what we're seeing. And then for those who care about the sediment information, it's fine to coarse sand with some other facts there. And here's just a little image of deploying it at the beach. Again, as I mentioned, you can see the uniformity in the alongshore, as well as it just takes 2 people to deploy this, which is makes it good for the conditions we like to sample in, which are quick, high wave energy events like storms, so we can get down to the beach quickly and get it in. Example of what the data looks like quick from that. Again, I'm going to convert all my pressure to pressure head in meters to talk about it. You'll notice this color code throughout. The blue are the sensors in the water, and the oranges and reds are the ones in the sand. And I'm just going to show you a little video of this, but we're going to talk about it first. So the top shows you 2 minutes of data, again, that same color code, and then the one on the left is looking at the vertical pressure profile. In time, we're going to look at time as we play the video, and then for this right panel, I've removed hydrostatic, so you can look at how it deviates from hydrostatic. That's what we're pinned at 0 there. As this plays, really quickly, you can see the black marker on top. We're going to go over a wave crest and go to the wave trough, and I've kind of highlighted the 4 important parts. We see these upper sediment sensors are deviating from hydrostatic, particularly at those crests, and versus the ones lower in the sand seem to match hydrostatic fairly well. And this has been important because these deviations from hydrostatic is actually what causes those vertical pressure gradients that we're interested in terms of what that shows for the sediment transport aspects. And again, I don't want to get too far into this because we did publish the paper on this, but we have compared those vertical pressure gradients that you calculate, and we can compare them to momentary liquefaction criteria and have shown that we believe momentary liquefaction is happening again. All of this is just to set up sort of what I'm going to get into next. As I kind of said, I've done lots of observations, but we've been shifting a bit into the numerical modeling side of the pressure propagating into the sediment bed. So that's what I've been working on lately now, which there are lots of boundary value problems that describe the wave-induced pressure within the sediment beds. And I'm going to focus on one today. Again, I'm going to try and speed through the math quick, but we can start with the governing equation with the which is a continuity equation for the soil skeleton. It's based on consolidation theory, so we assume our sediment bed is a porous medium, acts like a sponge, right? It can compress and expand as water goes in, there's pores, and then we can make a couple different assumptions. Again, I'm not going to go into it, but we can reduce this to a one-dimensional diffusion equation. You'll see that the framework is non-dimensional, but we have 2 parameters there, alpha and beta, which are dependent on hydrodynamic and geotechnical parameters. And then as well, it's independent on pressure, and then also looking at vertical, the Z is the vertical direction, and time. The PV is pressure at the bed versus the non-PV, regular P is just pressure in general. We can do a little intermediate variable, switch the variable a bit to make this an even simpler boundary value problem to solve, which is shown here. Again, we just have one variable to worry about, not those 2. And we can see that at Z, again, non-dimensionalized, which I've shown up here, at Z equals 1, which is our interface, we can actually, this is force for the time-varying boundary condition, so force from the pressure at the bed with that PV again. And now that we have the boundary value problem set up, thinking about solving this, so I use something called the Tidally project to solve this, which is, wondering what that is a way to spectrally solve differential equations. I linked the website there. This is all open source. It's written in Python, and it's fairly fast because it works in the spectral domain to solve these kinds of differential equations. I listed a couple facts here, but one of the ones I like, that I think makes it different, is that you can symbolically specify your equations and boundary conditions, so you can actually put in like P equals 0 at Z equals 0 when you're putting it in the system, which is interesting and different. So how this framework works, we have our boundary value problem. As I said, it's force from the pressure at the bed, so I use my observations from the pressure stick, specifically the one closest to the bed, to force it, switch the intermediate variable to that capital P, and then we put this into Tidally and go from there and look at the pressure in the seabed as a function of vertical depth, and then compare this back again to our observations at our other sensor locations, just to show you the framework there. I've done this for a couple different data sets we have. I'm going to show you a more interesting one today, but I guess I'm caveating with the ones that are less dynamic, so the times we don't see the momentary liquefaction or the high vertical pressure gradients, the model matches really well. So we're going to focus on a more interesting case today, specifically that same 2-minute time series I was showing you. So now we're looking at the same setup for our video here, with the pressure on the left and then the subtracting hydrostatic on the right, but now I've kept the pressure stick values in the gray and the new Tidally values in the colors. As I said, it's force from the bed, and then we look at pressure within the bed, so we don't have calculations for the ones in the water. That's why you only see the gray there. I'm gonna run this again. This was a little slower than the last one, but you'll start to see again in this upper sediment that the observations and the model deviate from each other, especially as you start to move through the wave crest. You see this one goes up here. You can see them start to differentiate, and then also the lower ones match better. So I'm gonna let it play out a little bit as we get to the larger wave crest. Sorry, Dad. So hopefully it's not too long, but trying to speed through. So see there's that big large deviation. I can definitely speed this up. I can look at these deviations also as a time series. So as we see that they both do deviate from hydrostatic, we saw differences from 0 in this bottom right panel. But we can plot that as a time series. So the top is our forcing time series at the bed, and then the lower panels, the gray ones, are showing you the difference from hydrostatic from each method, the pressure stick and the observations. So we do see they both differentiate, especially at this second sensor there with 16 centimeters into the sand, which is where we also saw the more dynamic vertical pressure gradients happening as well. To also convince you that how this compares between the observations and the model, if we compare those on top of that, that's the pink is now our field observations minus our model. Again, we do see good agreement, particularly at the troughs, but as we approach those large crests, we see some disagreement there. With the caveat that if you look at my y-axis, this is all still very small in terms of difference, in terms of magnitude of the difference, I should say. Continuing on, we can also look at more data in the phase space. So I'm going to do that quickly. So when we think of a phase space, we can transform our time series in time into phase. So now we're going to be focusing on the crest and the trough a little bit. So if you think of our plot here, we have the pressure on the x-axis with the mean removed, and then the time derivative of pressure up on the y-axis. And if you remember calculus, when our derivative goes to 0, we have a maximum or a minimum. So on the right, you're going to have a crest, and on the negative or smaller, so on the minimum side, you're going to have the trough. So and the waves will go counterclockwise. So you can do this for a bunch of waves and then average. So this helps us look at where in the wave phase we're seeing certain things. So there's going to be a color variable that will be what we're averaging. In this case, I'm looking at the observations minus the model. So we can see in general that we have higher crests, right, than troughs. So we have more data over here on the right, which you saw in the time series as well. And then those deviations, the larger ones, are happening right around the crest and less around the trough. It's interesting. So coming in quickly. Through all this, there's a greater difference between our observations and this numerical model when we see these high deviations from hydrostatic, which is those large vertical pressure gradients. And then similar, the differences are happening around the wave crest, again, with the caveat that it's less than 10% difference between the two methods. And then the ongoing work that we're working on is field experiments with all of this. So that's sort of push for all, as you kind of saw, I did a lot with the vertical, but looking to, we've designed 2 more pressure sticks that are an improved version, and trying to deploy them in the field to look at the horizontal pressure gradient as well as the vertical. That's ongoing. That's all I have.
Any questions? We have time for 1 or 2.
What's causing the difference?
That is an excellent question. So I think it is. So I have other examples that I didn't show here when we have smaller magnitude waves as well as less peaky waves. So I think with the nonlinearity of these specific waves, the large waves in general, the more dynamic nature of these large vertical pressure gradients we're seeing at this specific 2 minutes is what's not being captured in the model as well. Yeah, I don't know if I had a lot to show, so I was like, I don't want to show my not exciting example then, but
Sure.
exactly. Does that answer?
Well, yeah, I was going to say is that whatever equations you plugged into, what's it called?
Daedalus, yeah. I was saying it wrong for a while.
That was the diffusion equation.
Yep, it becomes a diffusion. You reduce it based on solid water equations.
Thanks first. Okay. Thanks, Melissa. What assumptions went into you had there were some assumptions. Are you simplifying enough that are leading to the deviations or discrepancies?
So I don't think so. So the simplifications we made is just to take that general consolidation theory and use it in ocean environments. So we assume that our domain is like partially saturated. It's not infinite. We assume like a limit on that. And then we also make some assumptions using Hooke's laws to relate that equation had velocity in it, but we related to pressure. So those are some of the main assumptions in actually reducing that equation.
You don't think that's leading to any of the
I don't-
simplifications are leading to it?
I don't think so. So there's been work with that same set of equations where they use sinusoidal waves, like looking at bores and singular waves numerically, and that those match fairly well. But they don't look at these sort of nonlinear continuous wave spectra. My opinion, as I think.
No, thank you. Yeah, I have follow-up questions, but I'll pass it over to Tony.
No, I'll talk to you afterwards so we can.
Okay.
Right. Well,
We
thank
can talk
you.
after talk too.
Thank you, Melissa.
Good afternoon, everyone. Like Adriana said, I work with Dr. Gabe Benegas on seafloor sediment characterization using acoustics. And today I'm going to show you some of our results from a Bayesian model we constructed for mass application to a large standardized data set. So first of all, what is this type of data and really who cares about it? So for those of you not into underwater acoustics, when sound travels underwater, especially at great distance, it will reflect off the seafloor. And the characteristics of the seafloor can change how that sound returns to the next spot that it's going. So who cares about this? The Navy is really interested in this because they have many acoustic models that tell them how sound propagates when they're trying to model whether it's enemy asset detection or their own communications underwater. But if we're looking at sediment characterization, people who might also be interested in this are benthic scientists who are interested in biological processes, chemical processes in the sediment, or geophysical properties of the sediment. So the data set we're using, it says a large standardized data set. So we're using NOAA fisheries data. So NOAA has a fleet of dedicated vessels who have transducers monitor their holes, actually a suite of transducers at different frequencies. And they go out and collect acoustic data in standardized methods. And they do this all over the US continental shelf. And they do this for the process of counting fish stocks. They can better manage the US fisheries. This data also collects the bottom return. And you can see that here. This is an echogram of the data. So that's what the seafloor return looks like. NOAA doesn't do anything for this with the seafloor return, but that's what we're trying to do here. So main takeaway from this is this is a standardized data set and is covering the whole US continental shelf. You can see over here, this is an example of the data density just offshore in New England, so our immediate area. All right, so the model that we're trying to fit the data to is a scattering model that we've augmented with a couple features. So it's a physics-based model, so we give it a independent variable, in our case time, from transmit of the transducer, and then it tells us what the intensity wave of the returning echo should look like. For the sake of this presentation, think of it as a black box where we give it all of these parameters, feed it a time array, and it gives us back an intensity array. So we give it transducer properties, water column properties, as well as sediment properties. And like I said, we augmented it. So we, instead of basing this off of mean grain size, how the model was originally designed, we've augmented it to include index impedance to relate a lot of the properties. Index impedance is really just a way to characterize acoustic hardness, so how well something reflects sound in the water column. And we've also used or augmented it with a density depth gradient. So how does the density change in the top couple layers of the sediment? Here's the equation for Iowa. It's essentially a relationship between the sound speed in the water, the sound speed of the sediment, and the density of the sediment. So the Bayesian inversion. So this is what's comparing the model to the data. So the Bayesian inversion, Bayesian means it uses a priori knowledge to bound the parameter space. So for our case, for our parameters, take IOI for example, we'll bound that in the realistic range we know. So it's not going to search negative infinity to infinity. It's just going to search, in our case, between 1.05 and 2.6. So that's the Bayesian part. And then this has some robust parameter exploration. So as it's searching parameter space, we run principal component analysis to inform how it explores that parameter space. And then the actual exploration of parameter space happens through parallel tempering. So for our model, we run 12 chains, and every iteration, a chain picks a new set of parameters based off where it is in parameter space. And we have 12 chains. 6 of them are low temperature, where they take very, very small steps through parameter space. They look at a very local area very thoroughly. And then we have high temperature chains, where they bounce all the way around parameter space and basically explore the whole thing. Then every iteration, the low temperature chains and the high temperature chains compare how well they fit to the data for the model results for their parameters. And if a high temperature chain finds a better fit than the low temperature chain, it will move the low temperature chain there. So that's a way that we can explore the whole parameter space, and we don't get stuck in a local area of good fit. We can actually look for the best fit all throughout the parameter space. And that's important because this is a problem where we can tweak a couple of the different parameters and get similar results. So we need to make sure we're thoroughly exploring this parameter space to make sure we're getting reliable results. All right, so for the inversion results I'll show you, we're still in the model validation phase. We're picking NOAA data that's by in situ ground truth taken of the seafloor. So for our case, you can see that we are off of Boston, actually. And this is what the data looks like along here. So on the y-axis, we have intensity of the seafloor return. So this is the reflected intensity of the sound coming back to the transducer. And then the x-axis is time, so the time from transmit. I said we augmented the model to work with index of impedance. So since the ground truth sample taken by USGS gives us a range of sediment, a range of grain sizes, we convert that to IOI using an established regression from Jackson and Richardson high-frequency seafloor acoustics. So the ground truth corresponds to an IOI just a little bit above 2. So we're looking at mean grain size, we're looking at fine sand. So the index of impedance is about 2. So for our initial results, this is after 100,000 runs, and these are plots of the final 20,000 runs after it began to settle and find the areas that it really liked to measure the data to. These are heat maps of the 3 frequencies that we were trying to fit. The black lines represent the data pulses, and then the heat maps represent the spread of the model results using all the parameters from those runs. So they're pretty close to fitting. They're not perfect, but they're getting pretty close to fitting the actual data. We can see with the data, we have 95% confidence intervals from how we compiled these pings. So they're just about touching all the spots on the data, which is what we're looking for. All right, so I have 2 plots on here. The left plot is a marginal joint distribution plot. So on the diagonal axis along there, this is histograms of the different parameters we're trying to fit. And for this, I've just selected 5 of the parameters. So we have index impedance. The next 2 just describe seafloor roughness. And the last 2 describe the gradient. And remember that for this, we only bound it in the physical bounds. So for index impedance, for example, it could search all the way from 1.05 all the way up to 2.6. But we see up here, is kind of hard to see down here, but the histogram of the last 20,000 runs, it settled down all the way to 1.6 to about 2.4. And then if we overlay our ground truth data, it falls just about right in there. So our inversion explored all the parameter space and settled on a value where ground truth is smack in the middle. So this is telling us that if we look at how the other parameters settled, we might be able to rely on these a little bit more. And then from these histograms, we can extract confidence intervals of how certain we are that these are the actual sediment characteristics. On the right-hand side, we have a density gradient plot. So the y-axis is depth starting at 0 going down. This is in meters. And on the right-hand side, or on the x-axis, we have sediment density increasing as you go to the right. So this is a plot of the inverted 2 gradient parameters that we have here. And this is what our inversion tells us the most likely gradient is. And our ground truth, we don't have measured gradient parameters for our ground truth, but this is consistent with ground truth written about in other literature, notably Tony Lyon's own paper back there. So what's the take-home message from all of this is that we can apply this inversion to a large standardized data set and get back sediment characteristics with the quantified uncertainty, which is what we're looking for. And we can move from a data density that looks like this, which is all the ground truth samples around Cape Cod Bay, to something that would look like this, which are all the ship tracks. So this would save both time and money because going to get in situ samples is really expensive and only limited in their extent. These are my references, and thank you all very much.
When you talked about doing the analysis in parameter space, you mentioned you reduced from minus infinity to infinity down to 1 to 2.6, which does allow you to explore the parameter space more. But it also provides an opportunity to look at the sensitivity across the parameter space. So you may find that if you go from 1.5 to 1.6, you get that big a change, but if you go from 2 to 2.1, you get that big a change. Did you do any of that, particularly in n-dimensional space? If you have 4 parameters, Did you do that? Has anyone done that sort of thing?
Like seeing, let me make sure I'm understanding. It's like basically what parts of each parameter make the greatest variability.
Exactly.
We haven't done that yet, no.
Okay. Has anyone else?
Not to my knowledge. Dr. Venegas, do you have any knowledge of anyone exploring that with these parameters?
I'm not totally sure. We know what they do to the waveforms, but we haven't done these formal sensitivities.
Right, thank you.
The priors that you're using, you talked about settling a prior on the plausible region for individual parameters. Have you considered, has anybody considered, the correlations between those physical parameters? Those parameters don't exist in a vacuum, and a value for one parameter may not be possible with another value for the other parameter, so you may have a system that just physically can't exist. Is that something you've considered or something you would consider?
That's definitely something we would consider. Right now, these parameters are mostly bounded by what our physical model can accept, essentially with how it models all of these physical characteristics. But that definitely is something to think about going forward. If we have like a low value here, that means that we have to exclude high values somewhere else for the pairings.
I'm curious, all this comes from National Marine Fisheries. In theory, everything's calibrated. I'm kind of wondering how sensitive that calibration is. Is this shape enough, or do you need the absolute value? Have you tried two different ships going over the same sea floor with nominally the same systems?
We haven't tried that yet, but that's the goal, because hopefully, these ships visit areas year after year. So we plan to hopefully compare and see both to validate each other, but also possibly track over time how the seafloor might be changing for other reasons. Andy?
Is that all the same ship, or are there multiple ships in there?
No, there are multiple ships. So this is about 4 or 5 ships. All have at least 3 frequencies, some have up to 5. So this is a compilation of 5 different ships.
Right. Any more questions after?
So as was mentioned, my work involves sediment flow interactions in the Hampton-Seabrook estuary, specifically looking at salt marsh environments and specifically tidally driven salt marsh environments. Before we start, I'd like to thank the USCRP for funding this program, as well as my committee members and PIs on this project, Dr. Tracy Mandel, Dr. Tom Littman, Dr. Dave Burdick, and Dr. Diane Foster. So before we get into it, let's figure out what a salt marsh is. Salt marshes are coastal wetlands found in the intertidal zones of estuaries characterized by the presence of photoautophores tolerant of brackish waters of varying salinity. They are separated into 3 parts: mudflat, low marsh, and high marsh. The mudflat is bare, while the low marsh and high marsh are densely vegetated. We talk about them frequently because of how important they are for our ecosystem services. So they offer incredible services when it comes to biodiversity, food webs, etc. What we're talking today is about coastal resiliency, so preventing flooding, as well as sediment trapping in general. One thing we've noticed is that salt marshes are very effective sediment traps, meaning that they are growing over time. They grow at roughly a rate of 2.58 millimeters per year. Unfortunately, as we are all aware, the ocean is also getting higher, so our average sea level rise is now at 4.17 millimeters per year. So what we're experiencing is something called the coastal squeeze, where our our salt marshes are drowning. So our low marsh is turning into mudflat, and our high marsh is turning into low marsh. There has been some research done on vegetated environments before, looking at sediment deposition and suspension. However, those have been done in just generic vegetated channels, not specifically in salt marshes. This is one of the first projects that actually set out a suite of arrays of instruments within the marsh and fully instrumented it. The 2 questions we'll be asking today and trying to answer are: how do turbidity and turbulent kinetic energy evolve across the marsh and throughout over tidal cycles? And as well as how does vegetation modify flow and contribute to sedimentation in the marsh? Our field site chosen, for you guys, you probably already know where Hampton-Seabrook is. But for those who are not aware, Hampton-Seabrook estuary is found in southern New Hampshire. It's a tidally driven salt marsh, which is characterized by narrow channels with distinct mudflats, low marsh and high marsh. The environment you see here over the time lapse is the environment where we were set out our array, so you can see them deployed right there. It's a salt marsh that will grow, that has a tide that is semi-diurnal and ranges in about 3.5 meters. So when at the highest spring tides, the water will come to about 2.5 elis. When it is low, it is completely in the channel. So the mudflat is bare. For this deployment, we set out 3 poles and we fully suited them all. So first we put out our YSI multi-parameter sondes, which took turbidity and conductivity and temperature data. As you can see with the range of water levels, one of our instruments was not submerged. Initially it did fail, so that worked out very well and we took it out. We ended up with 5 instruments. Next up, we put out our Nortec ADV vectors, which took velocity data in all 3 directions. We also had 3 OSS wave loggers. Those were equipped to measure and assist in flow characterization. And we also had, Nortec ADV as well, and Aquadot. And finally, I had a time-lapse camera, which is what took the video from before that was shooting onto the array. And that just allowed us to have visual data to match up with our instrumentation. Perfect. So 3 factors we'll be looking at are turbidity, the velocity spectrum, and turbulent kinetic energy. Starting with turbidity, it's a measure of suspended sediment. What you see here is just an example of what the data looks like. Next up, our velocity spectrum. So the reason we're looking at the velocity spectrum is because we're looking at turbulence. So when it comes to turbulence, we talk about the turbulence spectrum, which is right over here, which we can separate into 3 parts: the energy containing range, the inertial subrange, and the dissipation range. So up top is an example of the data that we had, and this is an idealized model of only turbulence. And what we're looking for is that negative 5/3 slope, which would point to an inertial subrange, which would point to turbulence. And finally, we're looking at turbulent kinetic energy as well, which is a measure of the intensity of turbulence in the flow. So starting to answer our questions, how do turbidity and turbulent kinetic energy evolve over tidal cycles? So first of all, turbulent kinetic energy drives turbidity. So we notice that there's a match up in the TKE and the turbidity as opposed to the current magnitude and turbidity, which we notice there's high values in the flood tide, low values in the slack, and a slight resurgence in the ebb. Next up, we have increased turbidity in the ebb, which as a result of large-scale movements. So actually, what we did is we plotted TKE the standard way, and then we took a TKE with a 10 to the minus 1 hertz cutoff to remove that that low-frequency data, and we found that we lost those little tails over here that showed us that resurgence in the ebb. So that heightened turbidity at the end of the cycle is actually due to larger currents and not to turbulence. And finally, we figured out that the marsh retains sediment. So as you can see here, we've got high amounts of turbidity at the flood tide and low amounts in the ebb, meaning that the marsh is actually accreting sediment, which is what we expected to see, and this is just confirming that. Next up, looking at how turbidity and turbulent kinetic energy evolve across the marsh, so spatially. First of all, we find that peak turbulent kinetic energy in the mudflat causes a peak of turbidity in the low marsh. So we've got a slight delay, high turbulence in the mudflat, and then a peak in the low marsh. We found also that turbidity was vertically homogenized in the low marsh, which is not something that we expected. And finally, we found that turbulent flow is most present in the incoming tides, which is likely due to the mean current. Next up, looking at vegetation and how it modified flow. So we discovered that there was an inertial subrange in all three locations in the vertical. So we didn't actually find it in the horizontal, meaning that most of our turbulence was vertical. This also indicated a gradual transition away from fully turbulent flow, moving into the marsh. So we had high turbulence in the mudflat that lessened into the low marsh and into the high marsh, which we can attribute to the stronger flows in the mudflat. Finally, looking at vegetation and how it contributed to sedimentation in the marsh. So we found that marsh vegetation attenuated flow, increased vertical turbulence, homogenized turbidity, and finally created an environment prone to sedimentation and of suspended sediment. So what's the story here? We found that strong flows on the bare mudflat created high magnitude of turbulent kinetic energy, which in turn caused the bed sediment to be suspended in the mudflat and then move over to the low marsh, get advected through that big, stronger current. That vegetation in the low marsh would then cause a dissipation of that the flow and creating vertical turbulence. And those weaker currents in the low marsh were allowing the sediment to sediment. In the high marsh, you'll notice I didn't talk about it here in the big story just because it was very rarely submerged by the instrument. So we had limited amounts of data. But what we can assume is that there was still stuff going on, and that maybe that weaker and shorter time that was spent submerged by our instruments simply indicated that the same thing was happening, it just didn't have as much resources. Thank you. Questions? Easy.
Presentation, I think you went through this pretty quickly. I was wondering if you could talk more about you had the graph with the vegetation, the size. Can you talk a little bit more about how you measured that and how, is that like a when?
Yes,
Is that throughout, or?
So all the vegetation data was taken by Dr. David Burdick. He went out into the marsh once in 2023, I believe in August, and then again in October 2024. The sedimentation, the sediment accretion data was taken using sediment plates. So essentially just kitchen tiles that were placed on the marsh. And then we also have stem density, which is cross-sectional density of the stems, which is taken by counting them and measuring the width.
So do you think that would change at the different seasons? Because that's not the same time you said.
It's not the same time. There could be some seasonal variation. However, in Dr. Burdick's professional opinion, it wouldn't change that much.